In the last lesson in this series, we learned a bit about system consolidation, the reorganization of a memory over time, so that the memory becomes stored more strongly in the cortex and it's retrievable without the requirement of having an intact hippocampus system. And that idea came about after studying patients like HM who had large sections of his brain removed. In this lesson, we'll look at this concept of allocation. So within a brain region, certain neurons, certain brain cells will be assigned to the storage of a given memory. Let's go to the hippocampus again. Let's say here's our little hippocampus, and the circles here would be neurons, brain cells in the hippocampus. And this is just a bunch of neurons. Now, we're not showing any of their connections or anything, but these are just neurons, and this is prior to a learning event. And the idea is, as we learn something, a certain subset of those hippocampal brain cells will respond to that particular learning event. And we're going to call this allocation. So the four in green here, they are the ones then that are going to be responsible for making a memory of that particular learning event. The other neurons are not going to be involved in making a memory for that event. That's what we're calling allocation. Now, let's add the cortex to the picture, and what we've done here is pulled out the hippocampus. Remember, normally it resides underneath the temporal cortex. So here we have the hippocampus, and we're going to say it forms a memory trace for the learning event. In other words, a certain set of hippocampal neurons are going to respond to the learning event, and then they're going to change in important ways. And a memory trace refers to those neurons that were activated by the experience, so they've been allocated, underwent lasting changes. That's the plasticity that we'll talk about in future lessons, and are later reactivated for successful retrieval of the memory. So here already the idea is whatever brain cells here in the hippocampus that responded to the learning event, they are going to be the same ones that will be reactivated when we retrieve the memory for that event. We're going to let this icon here, the little triangle, 3 brain cells and connected by these lines. That will be an icon for an episodic memory trace formed in the hippocampus, and the memory is robust, indicated by solid lines here, due to a significant increase in communication between those neurons. So we're going to say the neurons that took part in representing that episode, they're going to have strong connections with each other, forming a strong memory trace. Now notice, up in the cortex, we have 3 neurons as well, but there are dashed lines between them. And this is intended to represent that while these brain cells might have been activated by the learning event as well, there are weaker connections among this set of neurons. So we say this is a weak memory trace in the cortex. But again, some set of brain cells in the cortex are going to be allocated to forming a lasting memory of that episode. It's just the memory trace in the hippocampus is strong initially, and the memory trace in the cortex is weak initially. Now, in the last lesson, we introduced the concept of system consolidation. Now let's take a look at what that sort of means with our little brain picture here. So the idea is initially we have a strong memory trace in the hippocampus and a weak memory trace in the cortex. Neurons have been allocated in both locations. And what's going to happen with system consolidation is the hippocampus is going to be signaling those cortex neurons to strengthen the connections between them, thus forming a stronger memory trace for that learning event. So again, the idea here is that the processing of memory involves multiple brain regions and a transformation, a change in the memory over time. And this process is called system consolidation. It involves the hippocampus and the cortex. The hippocampus is teaching the cortex to make a stronger memory trace for the learning event. We could say that system consolidation transforms the memory from one in which the hippocampus is needed for retrieval to one in which it is not. Again, we see the importance of the hippocampus here. If you don't have a hippocampus, you can't make any new memories. But once you consolidate a memory, then the hippocampus will no longer be needed to access that information. We would say that's semantic memory, and it can be accessed without a hippocampus. And if we were to diagram that scenario, here we have the hippocampus has been removed from underneath the temporal cortex. Semantic memories, this will be our icon for semantic memories stored in the cortex. The brain has other retrieval systems that can access semantic memories without the need for an intact hippocampus.